So now let's look at the second step in deriving this estimate. So the first step was to break this parameter down into the product of two different terms, essentially using the chain rule of probabilities. So we first predict the rule, and then we predict the lexical item conditioned on the rule together with the head word. The second step is to use smoothed estimation for the parameter estimates of these two parameters we're left with. And so we'll apply exactly the same ideas we saw for language modeling, for example. So in this example, I'm going to use linear interpolation. So we're going to have two parameters, lambda1, lambda2 greater than or equal to 0, and lambda1 plus lambda2 is equal to 1. And what do I have here? I have two maximum likelihood estimates. So if we look at this first one, this is going to be estimated as the count of S SOR, so this is S headed by SOR, rewriting as NP VP with the second child VP as the head, divided by the count of S SOR. So that maximum likelihood estimate is basically an estimate of the probability of S SOR rewriting with this particular rule. Again, it's a very natural, simple, intuitive estimate. The second one is basically a backed off estimate that completely ignores the lexical information. So now we're going to back away from conditioning on the word SOR, and so we're going to have count of S goes to NP VP divided by count of S. Notice this is almost identical to the estimates you'd see in a regular PCFG. So we're essentially interpolating two different estimates, one which conditions on lexical information, which isn't present in the PCFG, and the other which throws away the lexical information. And by the usual arguments, this estimate will tend to be more robust in that the counts will be larger, we'll have fewer problems with counts being 0 and so on, whereas this estimate will be more detailed in that it takes into account lexical information, which is very useful. And by interpolating these two estimates, we get a balance, we get, in some sense, the strengths of both of these two estimates, robustness and also some sensitivity to lexical information. So now let's look at the second parameter, this parameter here, and we'll use a very similar method. Again, a smoothed estimate. I'm using parameters lambda 3, lambda 4, lambda 5 to distinguish these from lambda 1 and lambda 2. So again, we have lambda 3, lambda 4, lambda 5 greater than or equal to 0, lambda 3 plus lambda 4 plus lambda 5 is equal to 1, the usual constraints. And now let's look at these different maximum likelihood estimates. So the first one is basically, if we think about this schematically, if I have S SOR, I have NP VP SOR. This maximum likelihood estimate is going to be the ratio of two counts. The first count is just going to be the number of times I've seen this entire configuration. And on the numerator, I'm going to count the number of times I've seen man in this particular position. Okay, so this estimate is basically conditioning on the entire structure, the entire rule, and the head word SOR. At the second level, I throw away the word SOR and simply say, given I have this structure and I have some head word here, any head word, what's the probability of seeing man in this position? The final level down here is, given I have an NP, what is the probability that I have man as the head word of that NP? Okay, so we've gone from a very detailed estimate. This is basically saying what's the probability of man being the subject of the verb SOR. This one is saying what's the probability of man just being a subject, irrespective of the head word. And finally, this is just saying what's the probability of man being the head of an NP. And again, by the usual arguments, this estimate will be more robust, but it's much less detailed. This will be less robust but more detailed, and we attempt to gain the strengths of all these estimates by interpolating between these three things. So if we put this all together, we can see that this was our goal, to estimate the parameter for an entire rule. We first decompose this into a product of two different parameters, and we've estimated these using these smoothing techniques. And if you look back at all of the counts that we've used in this model, we've used everything from extremely detailed counts, the number of times man and saw are seen together in this particular configuration, to very, very coarse counts, things like the number of times I've seen S goes to NPVP. So we essentially have everything from the counts seen in estimation for a regular PCFG right up to these very detailed lexicalized counts. So that's basically it. That is basically how we can estimate the parameters of a lexicalized PCFG. So if we have a tree bank, we can just read off these counts and estimate the parameters in the way I've shown you. There are some other details which I'm not going to go into, but which are important in getting these algorithms to work really well. So let me just briefly mention them and give you a reference if you want to read further. One is that although I've shown you the case for lexicalized PCFGs in Chomsky normal form, it is important to deal with rules which have more than one child. So here I have an example rule from the Penn tree bank, which has 1, 2, 3, 4 children on the right-hand side of this rule. There are various ways of doing this. A very simple way is to binarize the rules. So we have a flat rule like this. I'm omitting the head words here for brevity. You can convert this to a structure like follows, where we have intermediate cases here. So this might be VP underbar or something, if we use VP underbar to signify an intermediate non-terminal within a VP. And so what we've essentially done here is binarize the grammar by adding these intermediate rules to build this structure. That's a very simple way of dealing with this. There are other ways which are more sophisticated and work slightly better. It turns out that in addition to associating a head word, for example, told, with each non-terminal, it's useful also to propagate up the part of speech information for that head word. For example, a V, or preposition, or PRP, this is a personal pronoun, such as him, or a complementizer. That gives you a little bit more information in these lexicalized rules. So you don't just have the lexical item, you also have the part of speech. And that can help. You can build more refined estimators using these smooth estimation techniques that can start to rely on these parts of speech. That can be very useful. Another thing is that you need to modify these grammars to encode preferences for close attachment. So coming back to this example, John was believed to have been shot by Bill. It's much more likely for by to attach to shot rather than believed. And we still haven't really addressed that problem. But there are modifications to lexicalized PCFGs which will allow us to learn those kind of preferences, and they are also very useful. If you want to read more about this, I'll post a link to a paper I wrote. This is actually my thesis work, which originates from about 1997, when I built one of these first lexicalized PCFG parsers. And this goes through the details of deriving a model that takes into account all of these different steps.